Yes, we can see it.
Okay. Well, I wish to thank to Ali for this invitation. I am sorry that I cannot be with you for several reasons, one of which is that I am actually still recovering from COVID. Anyway, distracted by COVID, you may have not, okay, let's see whether this works. You may have not noticed that the highest impact journals like Nature and Science have been flooded with papers on electronic nematicity. Nevertheless, this notion defies the common textbook knowledge of condensed matter physics. And given the abundance of high impact or hype impact discoveries and reports, I think it is prudent to question what, if any, of this you should actually believe. So in this talk, I will try to answer that question. There will be one more collateral benefit for you. More likely than not, like me, you have also encountered a particularly stubborn referee that is standing in your way to fortune and glory. And I will show you one strategy on how to fight back. Metals. Our understanding of metals was pioneered by Paul Drude more than a century ago. He imagined a metal as a gas of free electrons contained in a can. And this model was refined by Lorentz and Sommerfeld and later justified theoretically by well-known Landau's Fermi liquid theory. This theory successfully accounted for all of the key properties of metals, and in particular, the electric resistivity, which was attributed to scattering of electrons on impurities, structural defects, phonons, and other excitations. Now, indeed, one would expect a gas to be isotropic. To be more precise, all the physical properties of a given crystal, including the electronic conductivity tensor, effective mass, scattering rate tensors, they should all have the full rotational symmetry of the underlying crystal lattice. Now, we know of example where the rotational symmetry is spontaneously broken, and that's what happens in liquid crystals. Liquid crystals, when they were discovered, were also considered very strange because they flow like liquids, but are anisotropic like crystals. By now, the microscopic explanation of this is well known. Liquid crystals consist of rod-shaped molecules, and their attractive interaction, the cohesion, pulls them towards one another, favoring the closest packing. This is achieved when the rods align parallel to one another, and this is what breaks the rotational symmetry, and that's why liquid crystal, for example, polarizes light along one direction, etc. Now, much more recently, theorists envisioned electronic nematicity, which is analogous to the liquid crystal nematicity in the sense that there is a spontaneous breaking of rotational symmetry, but electronic nematic is spontaneous breaking of the rotational symmetry just in the electron fluid and not in the crystal. Needless to say, many people, including myself, first, when you hear it the first time, it sounds very counterintuitive. Because electrons in a metal run at enormous speed, like several hundred kilometers per second in cuprates, and they scatter on the femtosecond time scale in all directions, and they are not banana-shaped. So how could they possibly be nematic? And the emergency exit is that experimentally, cuprates are quite unlike ordinary metals. For one, the single particle approximation fails. Cuprates are strongly correlated metals. They are doped Mott insulators. And indeed,
they show many anomalous properties, including resistivity. Here is an example of a very good lanthanum strontium cuprate film grown by molecular beam epitaxy. And what you can see is that resistivity is linear in temperature up to 1000 Kelvin, which is not shown here. And this is quite unexpected because in a standard metal, resistivity should go as a third or fifth power of temperature, and then it should curve upwards, and then it should saturate at higher temperature. And more disturbing, if you use a Drude model and calculate the mean free path from this model, then you will conclude that at this highest temperature, the mean free path is shorter than interatomic distance. And now, if you go the other way to the low temperature, then in the sample, upon cooling down, the resistivity extrapolates to 0. And now, from the model, you would conclude that there are no defects or impurities. However, in lanthanum strontium cuprate optimally doped, we have 1 strontium 2 plus replacing lanthanum 3 plus, and the spacing of, so it's a charged impurity. And these charge defects, they are spaced at about 8 angstrom from one another. And the mean free path that you would infer even from the upper limit on this residual resistivity would be like 1,000 times longer. So what we infer is that at low temperatures, the electrons do not scatter on anything, while at high temperature, they scatter on nothing, on vacuum. And this, of course, is absurd. The only sensible conclusion is that the standard Fermi liquid theory fails spectacularly. The right plot here shows the dependence of resistivity on magnetic field strength, and it also becomes linear in high fields and doesn't saturate up to the highest field we were able to measure, which was 80 or 90 Tesla. And this also is unlike in ordinary metals, where it should be parabolic, and it also indicates the breakdown of the Fermi liquid theory. But that's not all. There are many other properties that are also anomalous. The ones that I'm familiar with are infrared absorption, electronic Raman continuum. Those in good metals die out on a scale of, let's say, 50 inverse centimeters, which may be like 4 or 5 millielectron volt. And the reason for that is that the momentum is well defined in one band and in the other band, and the moment of the quasi-particle, and the momentum of light is basically 0, so the transitions are vertical. And that's why with the momentum, the infrared absorption dies very fast in metals, and so does electronic Raman continuum. But in cuprates, both of these extend to at least 1 electron volts and beyond. And what that tells you is that actually the quasi-momentum is ill-defined or completely smeared out. And there are these other probes that I will not comment upon, but basically, whichever other way you probe it, the normal state, normal metallic state in cuprate is everything but normal. And this was in plane. All what I was showing so far were in plane properties, but if you look out of plane, things look even more strange. Basically, the cuprates, when you look with the light which is polarized parallel to the copper oxygen planes, they look like metals, maybe bad metals or strange metals, but metallic-like. But if you look perpendicular to it, they look like kitchen salt. They are insulators, strong insulators. And if you have read the book by Phil Anderson about high-temperature superconductivity, he has extensive discussion arguing that localization is a quantum interference phenomenon. So material cannot be Fermi liquid in plane and not perpendicular to it, or along the chain and not perpendicular to it. It's either 3D
very anisotropic Fermi liquid or not. While, okay, be that as it may, we have found experimental evidence. This is work in collaboration with Doug Natelson at Rice University by shot noise measurements, which directly measures the charge of the carriers that tunnel in tunnel junctions, which were lanthanum-strontium cuprate based. So what we found is that a large fraction of electrons remains paired deep into the so-called normal state. That means at temperatures well above Tc and at energies way above the superconducting gap. And this, of course, is a very tough challenge for any Fermi liquid or BCS type theory. Okay, so while ordinary metal cannot be nematic, perhaps a strange metal could. And with this motivation, many experimental groups looked for signatures of electronic nematicity in cuprates and other strongly correlated materials. And lo and behold, when you look for something specific, you will see it. And indeed, many groups reported seeing nematicity in various high-Tccuprates like YBCO, BISCO, lanthanum-strontium cuprate, using various techniques. Here, I will focus on only one that I have been directly involved with. We call it angle-resolved measurements of transverse resistivity. So here is a little theoretical background. Imagine that you have a material which is tetragonal, then its resistivity tensor can be drawn as a matrix, and this matrix must be diagonal because every direction is eigenvector for the current because of the rotational symmetry. And then this matrix will stay diagonal no matter how you rotate the axis. On the other hand, if the crystal is orthorhombic, then this matrix is only orthogonal, only diagonal in the so-called principal axis coordinate system. If you rotate the current direction azimutally, then the current vector is not eigenvector anymore, and that means that off-diagonal matrix element must be non-zero. And if you go through this trigonometry quickly, you will find that as you rotate the azimuth angle, the off-diagonal matrix element must oscillate with period pi. It means that they will have 4 nodes. And what you can also see from this expression is that longitudinal resistivity oscillate around some average value. And if the amplitude of this oscillation, delta rho, is much smaller than rho, the average value, then this oscillation may be buried within the noise. Because when we measure a lot of different devices, let's say in different angles, then inevitably there is some device-to-device variation due to lithography, etc. And therefore, your signal-to-noise may be not good enough to pick up nematicity if the amplitude of this, if the difference between rho and rho b is small. On the other hand, the transverse resistivity will show that clearly because if the crystal is tetragonal, then transfer voltage must be 0 by symmetry. And then as soon as you see non-zero transfer voltage, that indicates that the C4 symmetry is broken, that the system, the crystal is not purely tetragonal. And this must be true for every orthorhombic crystal. And for this reason, we invented a new technique that we call angle-resolved transverse resistivity measurement. So we grow a film, lanthanum-strontium cuprate film, by atomic layer by layer molecular beam epitaxy. Then we pattern it into what we call the sunbeam pattern. It looks like this.
it actually consists of 36 hole bars. And we run the probe current along the hole bar, and then we can measure the longitudinal resistivity between, say, contacts 3 and 5 or 5 and 7, and the transverse resistivity between 3 and 4, 5 and 6, or 7 and 8. There are 36 hole bars at 10 degrees from one to the next. Hence, we can measure the longitudinal resistivity at 72 pixels and the transverse resistivity at 180 pixels with the angular resolution of plus minus 5 degrees. And here are some representative results for 3 lanthanum strontium cuprate films, underdoped, optimally doped, and overdoped. In each film, you see that spontaneous voltage appears transfers to the probe current. This is just like a Hall effect, except that there is no magnetic field here. What transverse voltage means is that electrons feel some lateral force, which is compensated by electric field from the charges that pile up at the hole bar edges. Now, if the material is tetragonal, the resistivity tensor is isotropic and there is no lateral force. However, if the material is orthorhombic, then the conductivity is highest in one direction, and if you force the currents to flow at a different direction, then there must be a lateral force and hence a transverse voltage. So that's the idea. Now, as you can see here, that as a function of in-plane orientation, both the transverse and longitudinal resistivity show oscillations with 2 periods, 4 nodes. In this plot in upper panel, the solid red curve is the fit of the experimental transverse resistivity data to the function A times sinus of 2π minus alpha. But in the lower panel, the broken red curve is not an independent fit. What I did is just translated the top red curve down and to the left by 45 degrees. So the amplitude of oscillation in longitudinal transverse resistivity is the same, while the phases are shifted by 45 degrees, as our little theory predicted. We can also plot this in polar coordinates with the radial distance measuring the amplitude and azimuthal angle being the angle, and blue color denotes the positive and the negative values of the transverse voltage. And this looks like a cloverleaf pattern showing that the 4-fold rotational symmetry is broken. However, note that the crystal structure of the film is tetragonal. So one is tempted to claim a great discovery, electronic liquid crystal, a new condensed state of matter. But in America, people say if something is too good to be true, perhaps it isn't. And the bigger the claim, the more one needs to be cautious. And precisely because angle result transverse resistivity measurements are so sensitive, they will also pick up any anisotropy that is caused by some extrinsic factors. And for this reason, we assembled a list of all possible artifacts. Some of these are listed here. And then we check them and rule them out one by one through extensive and dedicated experimentation. We have been working on this for 16 years now. We first observed the effect in 2006, but first published it only in 2017, 11 years later. And in between was a tour de force exercise in material science. We did a lot of characterization by any and every technique available to us. And importantly, our accumulated statistics is enormous, with thousands of films and devices, perhaps without precedence in condensed matter physics. Characterization tool that we use every day in situ and in real time is electron diffraction. What it shows is that film is single crystal, no grains, no grain boundaries, atomically smooth, uniform, and epitaxially anchored to the substrate. What the latter means, since the films are very thin, typically 10, 20 nanometers, is that the film must be pseudomorphic to the substrate, meaning that the lattice constant of the film are the same as those in the substrate. We confirm this by read, but also by highest resolution synchrotron-based X-ray diffraction. if the substrate is tetragonal, so must be the film, and they are, as we verified. Now, in Hall effect measurements, there is usually some offset between the contacts. They are not perfectly aligned, almost never. And that means that you will pick up a little bit of longitudinal resistance, even if you are nominally measuring transfers. To show that this is not indeed the case of the nematicity we observe, there is a simple argument, which is a doping dependence. We studied many films, thousands of films, and they are all patterned with the same lithography mask, which means that the contact misalignment must be the same in every film. However, we found that both the amplitude of the nematicity and the orientation of the nematicity actually depend on doping strongly and systematically and smoothly. Here is the same thing except magnified by a factor of 100. What I mean by that is that here we have used a technique that we call combinatorial molecular beam epitaxy, meaning that we have deliberately created a small gradient of strontium along this central bar. The variation is about 4% on 1 centimeter, which then translates to the doping changed in the extremely fine increments, 1% of 1% for 1 pixel to another. And you can see that there is systematic and linear dependence on doping. And that, of course, rules contact misalignment and pretty much any other scenario that is based on some random extrinsic effect. Rather, I think this points to some subtle changes in the band structure and Fermi level with doping. So we have ruled out the contact misalignment, but are the contacts sonic? Schottky barrier, contact could fool you, as people who do this type of measurement know well. And for this reason, we check this routinely for each contact, longitudinal or transfers in each of the thousands of devices that we have measured. And all the contacts are indeed ohmic, and the contact resistance is in fact quite small. This may sound simple, but it took much experimentation until we developed a robust recipe to fabricate low resistance ohmic contacts to cuprate films. Another important test is temperature dependence of the amplitude and orientation of nematicity. What you can see is that C4 symmetry is broken already at room temperature, and that implies that the resistivity tensor is always orthorhombic, even though the films are tetragonal. But as or more important, the orientation of the easy direction, the direction of the highest conductivity, is not aligned with the crystal axis. And it even rotates with temperature. And that shows that an anisotropy that we observe in transport is essentially uncoupled from the lattice. That means that it is purely electronic. Another very incisive probe that we have added recently is transverse magnetoresistance. In zero field, the transverse resistivity has a peak near Tc. When we apply a magnetic field, the resistive transition fans out like this, and the peak in transverse resistivity is suppressed by an order of magnitude. The transverse conductivity increases by 1000%. And for this reason, in analogy to the well-known colossal magnetoresistance, you may call this colossal transverse magnetoresistance. Interestingly, in this sample, at this field, we see essentially no magnetoresistance in the longitudinal channel. But you can also see that the direction of the orientation of the director changes with temperature. In zero field, when you go from room temperature to Tc, it rotates by about 45 degrees. But when you put a magnetic field of 6 Tesla, it then rotates back to
the high temperature zero field orientation. And obviously this cannot come from the crystal structure because it doesn't change as a function of temperature, nor for any other random extrinsic factors. Another possible extrinsic factor that we know is there and we know breaks the symmetry is misorientation of the polished surface. No matter how much money you offer, you can never purchase a substrate that is polished with a perfect alignment to a crystallographic plane. Typically, they miscut the orientation by 0.1 to 0.5 degrees. And for this reason, the best substrate will still have some terraces on the surface, which are 1 unit cell tall and maybe a couple of 100 nanometers wide. The terrace steps are 1 unit cell tall. And these steps and terraces, they break the T4 rotational symmetry of the substrate and of the film because the film grows epitaxial on top of the substrate. To check whether this could be the explanation of the transport anisotropy we observed, we studied films of the same composition, like optimally doped, and on a substrate with different miscuts. We measure every substrate before the film growth by AFM, atomic force microscopy, and we determine the orientation of the steps in the film. Then we grow film, then we do AFM again, and we compare them, and lo and behold, the steps in the film are the same as the steps in the substrate. But these three substrates have steps at very different spacing and also different orientation. And nevertheless, the amplitude of the nematicity and even the orientation of the director are about the same. That means that these steps do not matter really when it comes to nematicity. And since we know the miscut angle, we can calculate, we know the in-plane and out-of-plane resistivity, we can calculate what effect would we expect. And indeed, it's like 2 to 3 orders magnitude smaller than what we experimentally measure. So that's not the explanation either. What else? Could it be due to strain? Because yes? Okay. The question is whether it could be due to the orthorhombic distortion and strain. And we varied both by using substrates with different lattice constant, like lanthanum strontium aluminate and neodymium gallate. Lanthanum strontium aluminate is purely tetragonal, while neodymium gallate is orthorhombic, about 1% difference between A and B. So it's a large orthorhombic distortion in by crystallographic standard. But as you can see, the lattice distortion is larger by 1 or 2 orders of magnitude, but the amplitude of nematicity is almost the same in films grown on lanthanum strontium aluminate, which is perfectly tetragonal, and in these lanthanum strontium cuprate films, which are very, very orthorhombic. The only difference is in the orientation. And this also points to purely electronic origin. Okay, the final suspect on my list is lithography. It is conceivable in principle that some steps in our lithographic process may introduce some asymmetry into devices. And to test and rule this out, we develop a different technique that completely avoids any lithography. Rather, we use micro machine shadow mask and deposit gold contacts through the openings in the shadow mask in a circle like this. And then we can use the 2 orthogonal pairs of contacts, like these 2 for the current and these 2 for the voltage. And then we can rotate that in steps of 10 degrees. And this is what you get. It's the same sinus 2 phi sinusoid as we see in films that were lithographically patterned into sunbeam. We have done this with films which were square. We etched also away the outer perimeter to make it a disk, and we have done this with bulk single crystals, so they're not even thin films. And we always see the same effect. And finally, as another logical check, we perform the same type of measurement using the same mask on other materials, quite a few. What is shown here are two, strontium ruthenate and titanium. Strontium ruthenate is like cuprates, a strange metal, strongly correlated. And indeed, we have observed an even larger nematicity signal. This is strontium 2 ruthenium 04, 214 structure. And in contrast, in titanium, that's this purple curve and purple line. It's completely flat. There is no signature of oscillation whatsoever on this scale. And this is another logical check because it rules out artifacts from the experimental setup or lithographic mask, substrate, etc. Okay, so far I have discussed a small subset of artifacts that we have actually considered, examined, and ruled out. And you will find much more in the article that I'm preparing for the conference proceedings. I will take a bet that whatever you can come up with, we have already thought about it and we have experimentally ruled it out. I think that burden of proof is now with the skeptics. It is not enough to hand waves and say disorder or strain. You need to propose a concrete and detailed model and show that it is consistent with all the experimental facts that I've shown and more. So in summary, cuprate superconductors are strange metals. They defy the standard textbook description of metals, which is based on the Drude model and the Landau Fermi liquid theory. Moreover, I think I have made a strong case that cuprates are indeed electronic nematics, that the rotational symmetry of the electron fluid is lower than that of the underlying crystal structure. However, before making such a bold statement, one must systematically rule out any conceivable experimental artifacts and possible extrinsic factors that may break the crystal symmetry. And this calls for some meticulous material science, employing a range of material characterization techniques and studying comparatively and systematically a large set of samples. So in the end, you might ask, why should I care? Well, for one thing, this calls for a critical re-examination of some textbook chapters on metals. Apparently, some metals are qualitatively different from a Landau Fermi liquid. And next, it is quite unlikely that the onset of superconducting coherence could magically restore the full rotational symmetry. In that case, the superconducting state must also be nematic. And indeed, we have gathered some experimental evidence, not published so far, that the superconducting fluctuations first develop in one direction and actually along a oxygen copper implant bond direction. And this is very hard to reconcile with the standard BCS theory, which postulates Fermi liquid normal state. In any case, this very tightly constrains the correct theory of high-Tc in cuprates. It informs on the character of the pairing interaction, which appears to be anisotropic. Note that this is quite unexpected. If the crystal is C4 symmetric, then so must be its electron band structure, the spectra of phonons, magnons, other excitations, as well as their coupling. So this may prove to be a crucial issue. Let me end up with some open questions. Good experiment, answer one question and then open many more. Eventually, we would like to know what is the microscopic mechanism of electronic nematicity. I have shown no evidence, no hints to that.
How is this related to other strange metal properties? How is it related to high temperature superconductivity in cuprates? Can we manipulate electron nematicity, increase it, decrease it, perhaps raising TC and JC in this way? And what we can learn by comparing cuprates to other materials that are showing electronic nematicity, strange metal, and other unconventional properties. Thank you so much.
Thank you, Professor Bozovic, for this excellent presentation. Now we can take questions from the audience, if there are any.
Good night, Ivan. This is Amit Kern. I don't know if you can see me. Very beautiful experiment, and I have absolutely no question that the experiment is correct. I just want to suggest something that maybe you considered already and maybe not. Even in the overdose side, there are about 80% of spins that are free. You dope a magnet, LSCO. Is it possible that the longitudinal current somehow polarizes the spins and you actually get a Hall effect from internal magnetism?
Okay, so, you know, what is, my talk was just trying to convince you that electronic nematicity is real, because there are still people who don't believe it. And that was my fight. What is the microscopic mechanism? I do not know. But all I'm saying is that it is intrinsic. So every lantern strontium cuprate, every device shows this effect without a single exception. Yes, something must be anisotropic there. I think that we have hints that there is anisotropic electron. Okay, so my guess is that it comes from electron-electron correlations, which of course involve spin and whether spins are parallel or not. There is this pairing that we see well above TC and also well above the outside of the superconducting gap. Now, we also know, you're right there, that even outside of the superconducting dome, there are still antiferromagnetic correlations. They are short-lived and with a very short coherence length in space. So we have done this experiment with Mark Dean and John Hill about 9 years ago, Nature Materials 2013. What we looked there using GRICS is the Magnon spectrum. And the Magnon spectrum basically doesn't change from undoped to overdoped metallic non-superconducting sample. What changes is the lifetime. So the peak becomes broader, the lifetime becomes shorter, but the magnitude doesn't change. So yes, there are antiferromagnetic correlations. Is that, just saying that is not enough. I think it's a good starting point, but one has to work out how can that break the rotational symmetry on microscopic scales. Our sunbeam is like 5 millimeters. So there is something very macroscopic happening.
Any other questions? Okay, there's one more over there.
Yes, Ivan, I, of course, as you know, believe all your experiments, and this one is no exception. But I have a terminological question, and
yes.
It is there is a well-known instability of the Fermi sphere, quadrupolar deformation, which is called the Pomeranchuk instability.
Yes,
now,
right.
Would you call a system with a Pomeranchuk instability a non-Fermi liquid, or is it still a Fermi liquid for you?
Well, it's a semantic question, and whatever majority accepts and uses
So do I. I have no preference one way or another, but certainly in the original, formulation, Pomeranchuk instability goes. It is not anymore a single particle description. You have this, pair entanglement in some sense, and maybe more than pairwise. So whatever majority says, typically when people say Fermi liquid theory or Drude model, they don't invoke Pomeranchuk instability. Is that a possibility here? Yes, Pomeranchuk instability may be operational here, but Pomeranchuk instability will, for example, deform the Fermi surface along X and along Y. But these two will still be degenerate. Something has to break that degeneracy here, and on a microscopic scale, like 5 millimeter scale. So maybe it's something much more general than that.
Thank you. I would just like to
right. And okay, Pomeranchuk instability, I'm not sure that would explain, for example, what we see in the infrared, what we see in Raman, what we see in tunneling, what we see in NMR, what we see in transport. It will have to be, very strong. And then presumably ARPES would pick it up. And so far they didn't. They don't see any nematicity between, X and Y.
Okay, thank you.
Okay, yeah, I think there's one more question
just
from
sort
our
of
moderator.
like to make a comment. Ivan, I wish that you were here because I'd love to talk more with you about this in person, and your talk was fabulous. Thank you very, very much. We used to disagree on nematicity, and I think we're on the same page now. But in response to the
yeah, well, I think it works in favor of my talk because Laura is my witness, and so is Seamus Davis, that I was very vehemently opposing it as long as I could. It took me like 10 years to say, okay, it's a hammer to the head. I see no way how I can wave this away. It just didn't want to go away.
Science wins, but I just
I think it's real. I think it's real.
I just wanted to add one thing, which was that one of the questions was about Pomeranchuk instability. There's two main theories about what causes the nematicity, and one of them is spin-spin correlations, and the other one is orbital ordering. And I was involved in orbital ordering. I actually think they're both correct, and this was for the nematic phase in the iron-based superconductors. And so, so I'm actually having trouble hearing you because the speakers are placed funny, Ivan, but maybe it's my own hearing. Yeah, okay. But I just wanted to, so sometime we can talk about these two different theories and compare your CUPRATE data to some of the old iron-based superconductor data. But it was very, very, very nice. Thank you.
Oh. Well, I think different, the transport measurement that I have shown here will not answer that question. If we are talking of orbital ordering, I would more hope that the state-of-the-art X-ray scattering experiment like RIX and things like that may detect, for example, orbital ordering if it's present. As for the Pomeranchuk instability, off top of my head, I don't know a good experiment that would directly probe that, but we'll think about that.
Yeah, we'll discuss it sometime, but it was just a great talk. Thank you.
Thank you.
Okay, thank you for all the questions and comments. I think now we continue.
Let's thank Ivan, Professor Bozovic again.